In this lesson, we are going to continue our study of Taylor and Maclaurin series. So let's start by reviewing some common Maclaurin series. So the first one that you saw was the series for 1 over 1 minus x. And that you can think about as a geometric series where a is equal to 1 and r is equal to x. And in that case, you found that that function is equal to a sum from 0 to infinity of x to the n. Now, in expanded form, that is 1 plus x squared plus x cubed, etc. And because this is a geometric series, this will converge if the absolute value of x is less than 1, which means our radius of convergence is 1. Then we use the definition of a Taylor series to find series for e to the x sine and cosine. So e to the x's series is a sum from n equals 0 to infinity x to the n over n factorial as an infinite sum that will look like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. This has radius of convergence infinity. And then a sine of x is all of the odd powers, and it's an alternating series. So this one will start with x, and then be minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, etc. That also has radius of convergence infinity. And you can verify that for both of those functions using the ratio test if you wanted to. So we have the sum from cosine is the sum from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So when you input 0, this will be 1. Inputting 1, we're going to have minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, plus stuff, radius of convergence infinity. Inverse tangent, we learned this infinite series in a previous section. We discussed power series before we even knew what a Taylor series was. So the difference here between inverse tangent and sine is that there is no factorial there, but they will look quite similar. 1 minus x cubed over 3, x minus x cubed over 3, plus x to the 5th over 5, minus x to the 7 over 7, etc. Now the fact that that denominator is not factorial makes quite a difference in the radius of convergence. This radius of convergence is actually just 1. You could verify that using the ratio test, and we verified it when we found this series because we integrated something that was a geometric series. Natural log of 1 plus x is one series that does not actually begin at 0. This should say it begins at n equals 1. If you were to make this series start at 0, it would look like this. Be the sum from 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. So that's equivalent to the previous series. In expanded form, this would be 1 x minus x squared over 2 plus x cubed over 3, etc. And the last one, this is called the binomial series. And in this case, 1 plus x to the k is given by k choose n, x to the n. And it's easiest to think about this one in expanded form. This is 1 plus kx plus k times k minus 1 x squared over 2 factorial plus k minus 1, k minus 2 over 3 factorial x cubed, etc. That has radius of convergence r equal to 1. So find the Maclaurin series for the following functions. I don't want you to actually find derivatives in this case. What you should do is use the series that you know. So we know how to find a series for arctan. So we'll do x to the 5th times whatever arctan's series is with x squared plugged in. So that's the sum from n equals 0 to infinity, negative 1 to the n, x squared to the 2n plus 1 over 2n plus 1. All right, that's negative 1 to the n. Now those exponents multiply, giving us x to the 4n plus 2 over 2n plus 1. And now this x to the 5th can distribute, and when you do x to the 5th times x to the 4n plus 2, those exponents add. And we have the sum from n equals 0 to infinity, negative 1 to the n, x to the 4n plus 7 over 2n plus 1. If you do try to find the Maclaurin series using the repeated differentiation looking for a pattern, you will get the same answer. It's just not going to be very pleasant to do so. All right, find the Maclaurin series for x squared times ln of 1 plus x cubed. So we have a Maclaurin series for ln of 1 plus just x. We can plug in x cubed for x. So x squared times the sum. Ln is the one series where they start it at 1. Negative 1 to the n minus 1. Will be x cubed to the n over n, giving us x squared times the sum from n equals 1 to infinity, negative 1 to the n minus 1, x to the 3n over n, and multiplying the x squared through those exponents add. We have the sum from n equals 1 to infinity, negative 1 to the n minus 1, x to the 3n plus 2 over n. Now, so far, all of the Maclaurin series that we've found when we've had stuff, we've had to like a polynomial multiplied by something that has a series expansion. Now, what might happen if we had two things that has series expansions? Now, this isn't going to be so easy to distribute anymore. So, sine x is the same thing as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. E to the negative x will be 1 minus x plus x squared over 2 factorial minus x to the 3rd over 3 factorial. And while theoretically I'm sure you can do distributions, so it's going to get really nasty really quickly. First distribute the x, then the negative x cubed over 3 factorial, then the x to the 5th. It's going to take a long time. So I'd like you to find the first 3 non-zero terms in this series by doing massive distribution. And it helps to just keep track of it. Hopefully the first 3 powers will be a first power, a second power, and a third power. So first distribute this x. So I can color code this to make it a bit easier. All right, that gives us x minus x squared plus x cubed over 2 minus x to the 4th over 3 factorial is 6. And there'll be some other stuff that comes later. Hopefully we won't need it because you only need the first 3 non-zero terms. Then distribute the negative x to the 3rd. Well, negative x to the 3rd over 3 factorial times 1 will be minus x to the 3rd over 6. Multiplying this by this x will give us a minus x to the 4th over 6. And then multiplying by the x squared over 2 factorial will give us minus x to the 5th over 6 times 2 will be 12. Okay, and everything there is going to powers bigger than 5, so we don't need to worry about them for only caring about the first 3 non-zero terms. And the question is do we care about what happens when you distribute x to the 5th? And the answer actually is no, because the lowest power you're going to get will be x to the 5th over 5 factorial times 1. So that's going to be minus x to the 5th over 120, or plus that. And everything else is going to have larger powers. So your first 3 non-zero terms will be x minus x squared. And then you've got to combine these two like terms. So getting a common denominator, that's 3x cubed over 6 minus x cubed over 6 will be 2x cubed over 6 positive, and then plus some higher order stuff. So that's the same thing as x minus x squared plus x cubed over 3 plus some higher order stuff. So the first three non-zero terms are those, x minus x squared plus x cubed over 3. And so that will occur when you have two things that have infinite series expansions multiplied by each other. Polynomials is a fact we've kind of been glossing over, but they are their own series expansions, because when you take repeated derivatives of polynomials, if you try to say find the Maclaurin series, you're going to have terms after some time their derivatives end up being 0. So in that case, the Maclaurin series are actually finite series. Now, if you thought that multiplication was complicated, division's also pretty not fun. So we'll just do one so you see how it works. So tangent is sine divided by cosine. Okay, so sine, the first few terms are x, and then the next one is minus x cubed over 3 factorial. Well, that's 1/6 x cubed. And then next is x to the 5th over 5 factorial, which is 1/20th, 1/120th x to the 5th minus more stuff. Hopefully that's all we're going to need. And we're dividing in 1 minus 1/2 x squared plus, now 1 over 4 factorial is 24, 1/24th x to the 4th, and more stuff. And we have to do polynomial long division. So what you think about is, what do you multiply this one by to make it match that x? And the answer is x. So that's x minus 1/2 x cubed plus 1/24th x to the 5th, and you take that away. And this cancels the x's, and without spending too much time dealing with the fractions, we're going to have negative 1/6 plus 1/2, which will be 1/3 x cubed, and then 1 over 120 minus 1/24th will be negative 1/30th, plus more stuff. Then you think, what do you multiply this 1 by to make it match that 1/3 x cubed? And the answer is 1/3 x cubed. So we'll have 1/3 x cubed minus 1/6 x to the 5th, and then plus some higher order stuff. Now those cancel, we get negative 1/30th, actually plus 1/6, which is 2/15, plus more stuff. And you say, okay, what does 1 multiply to make it match 2/15? Well, the answer is 2/15. Minus stuff, take it away, and you're done. You have the first 3 non-zero terms. We can also use Maclaurin series to estimate definite integrals and to integrate functions for which our techniques of integration don't work. So first we're going to find the antiderivative of sine x to the 4th as a series, and then we're going to use that series to estimate this definite integral correctly to 4 decimal places. So the integral of sine of x to the 4th is the same thing as the integral of the sum, n equals 0 to infinity, negative 1 to the n, and x to the 4th gets input into the Maclaurin series for sine. So that's x to the 4th to the 2n plus 1, all over 2n plus 1 factorial. And before you anti-differentiate, you have to express that as x to a single power. So that's going to be x to the, well, those exponents multiply, which gives us 8n plus 4 over 2n plus 1 factorial. Now the antiderivative, the negative 1 to the n and the 2n plus 1 factorial, there's some kind of constants. So what you're actually antidifferentiating here is this x to the 8n plus 4. And the antiderivative of x to the 8n plus 4 is x to the 8n plus 5 over n plus 5. So you have the sum from n equals 0 to infinity, negative 1 to the n, x to the 8n plus 5 over 2n plus 1 factorial times 8n plus 5. And there would be a plus c because technically it's an indefinite integral and you don't know that that constant is 0. Now we're going to use this result to approximate the integral from 0 to 1. So the integral from 0 to 1 of sine of x to the 4th, that will equal this series with first 1 plugged in. Well, that's going to give us the sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1 factorial times 8n plus 5, because 1 gets input for 8n plus 5, and that's just 1. And then you input 0, which is just 0. All right, now this is an alternating series, so we're going to use the AST remainder theorem to figure out how large we should choose n so that we have an error that is less than 0.40 and a 5. So we need the absolute value of the remainder, which is less than or equal to the n plus first term, to be less than 0.00005. So let's figure out what that n plus first term will be in general. So that will be 1 over 2 times n plus 1 factorial 8 times n plus 1 plus 5. We need that to be less than 0.00005. And that's the same thing as saying 1 over 2n plus 3 factorial times 8n plus 13 has to be less than 0.00005. And you test various n's until you find an n that produces an inequality that is true. And the first n that I found was n equals 2. So that tells you that you can approximate your integral, which I'm going to call I. It'll be about equal to a sum from n equals 0 to 2 of negative 1 to the n over 2n plus 1 factorial 8n plus 5. And inputting those n's, what this will be, so when you input 0, you get negative 1 to the 0, which is 1, over 1 factorial, which is 1, times 5, so 1/5. Inputting 1, we're going to have minus 1 over 3 factorial times 13. And inputting 2, we're going to have positive again, 1 over 5 factorial. 16 plus 5 will give us 21. So add up those first 3 terms and you get that this integral is approximately equal to 0.1875763. And one more final application of series is you can use this to evaluate limits. Now, technically with this, you could use L'Hopital's rule, but there's a very, very good reason why you don't want to. The fact that this is x to the 5th means you may have to do L'Hopital's rule 5 times. And the derivative of inverse tangent is easy on round 1, as in its derivative is 1 over 1 plus x squared, but past that point, it starts to get a little bit more tricky to take derivatives of that over and over and over. So here's how you can use a series. You're going to have a lot of cancellation of terms. So you have the limit as x goes to 0, x cubed minus 3x plus 3 times Let's input what the series expansion is for inverse tan. Well, that's x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, etc., all over x to the 5th. And then distribute that 3. We have x cubed minus 3x plus 3x minus x cubed plus 3x to the 5th over 5 minus 3x to the 7th over 7, etc., all over x to the 5. And notice that this x cubed and that negative x cubed cancel, as do this negative 3x and that positive 3x. And now every single term is divisible by x to the 5th. So like 3x to the 5th over x to the 5th will just give you 3/5. 3x to the 7th over 7 will be minus 3x squared over 7. The next number would have been 3x to the 9th over 9. Well, dividing that by x to the 5th, we're going to get plus 3x to the 4th over 9. And you see how that pattern keeps going. And every single term that's coming up, since you're going to 0, every single term is going to be 0 except for this first one, which is 3/5. So another application of these sequences and series is to use them to evaluate limits when you could potentially use something different, but maybe that something different like L'Hopital's rule isn't going to be so nice.